So, paper 2, and this paper 2 is beginning with a question on forces and the extension of a spring. This is a short section of P10, in fact, as one lesson, and a required practical as well. So, in this experiment, what is happening? A student investigated the behaviour of springs using the method below and presumably this equipment in figure 1. Number 1, suspend a spring from a clamp stand, as you can observe below. 2, measure the length of the spring, so the entire spring. 3, apply a force to the spring by attaching a 100-gram mass hanger to the spring. 4, measure the extension of the spring. And 5, add a 100-gram mass to the mass hanger and measure the new extension of the spring. Repeat step 5 another 3 times. So in this experiment, we are simply loading up masses onto this mass hanger, and we're seeing how much the extension of the spring changes. Note that we are looking to find the extension of the spring here. That is its new length in comparison with its original length. So 1.1 asks us what the independent variable in this investigation is. So the independent variable is what we are changing. And in this experiment, we are actively changing the mass on hanger. You could put, alternatively, weight of masses, or you could put force acting on spring. All 3 of those should be justifiable and acceptable answers. That is what we're changing in this experiment. 1.2 wants us to give one control variable in this investigation. Now, control variables are all other variables in this experiment apart from the one we change and the one we measure. Remember, in a scientific experiment, what we want to do is see how one thing is affected by changing one other thing. All other things that could affect this must be kept the same. So for this, although it's a slightly shabby answer, you could say same spring used. I think the best one, though, for this would be we must measure between the same points on the spring. What do I mean by that? Well, our measurements are no good if we measure from different points on the spring each time. So, for example, I might measure from here between the beginning points of 2 loops. If I did that once, I need to do it every single time. I can't measure that one time and then I can't measure from the top of the spring down to the bottom of the loop the next time. That wouldn't be right. I haven't controlled the length of the spring that I'm measuring. Okay, so 1.3, each 100-gram mass provided 1 Newton of force on the spring. The second student's results are shown in table 1. So table 1 has versus force, so this is going to be the, remember, 100-gram mass provided 1 Newton of force on the spring, so this is 100 grams, 200, 300 grams, so on, 500 grams. Now we have the extension of the spring at each length. I can already see an anomaly here. Doesn't fit with the pattern of the data. And then lastly, they've repeated that and calculated a mean. So calculate the mean extension at 5 newtons. Well, 5 newtons is here, and we have repeat 1 was 10 centimeters extension plus 10.2 centimeters plus 10.2 centimeters, and I am going to divide that by 3 as I have 3 readings. So 20.4 plus 10 is 30.4 centimeters all over 3 is 10.13 centimeters. Note, however, we are told that we must give our answer to an appropriate number of significant figures. Well, what is appropriate here? Let's have a look at the table. All of these values up here have been given to two significant figures. Therefore, we should do the same thing. But in this case, what I'd say is important is that you have this one decimal place here. So it would be appropriate, and we keep this constant in the table, we'll try and use the same number of decimal places. It will be appropriate for us to give 10.1 centimeters as our mean extension. 1.4 says one of the results in table 1 was anomalous. In fact, I pointed that one out already. So when we had a 300 grams on the mass hanger, we had an extension of 6 centimeters, 12 centimeters, and 6 centimeters. This 12 certainly appears to be anomalous. How might this have occurred? The likelihood here is the student measured the spring length, or the student recorded the spring length in total rather than just the extension. This is a common error in this experiment, or a reason for anomaly, rather than just the extension. Right, 1.5. The student plotted a graph of their results and drew a line of best fit. The graph is shown in figure 2. Mean extension, force. We've got a nice straight line and it passes through this point 0, 0, otherwise known as the origin. A straight line through the origin. Complete the sentence to describe the relationship between the extension of the spring and the force applied. The extension of the spring is something to the force applied. Well, whenever we have a straight line through the origin, our two quantities are directly proportional. They increase at the same rate. 1.6. Write down the equation that links extension, force, and spring constant. So, for short, this is one that we have to learn. That's why you get a mark for it. F equals KE. And that you would have to write it in full, and you must do this. Otherwise, you're at risk of not obtaining the mark. Force equals spring constant times extension. So extension is how much longer the spring is, typically quoted in meters. The force in newtons is the weight pulling down on the spring, for example, and the spring constant in newtons per meter is a measure of how stiff the spring is. Some springs are easy to squash and stretch, some are more difficult to squash and stretch. That's what the spring constant tells us. So, calculate the spring constant of the spring used by the student. Well, if force equals spring constant times extension, then spring constant equals force divided by extension. To demonstrate that using algebra ever so quickly, if this is our equation and we want to find the spring constant K, let's divide this side by E, and I must divide the other side by E as well. This is an equation, these cancel out, and the spring constant is equal to the force divided by the extension. The force, we're told, is 2 newtons, the extension 0.04 meters, 0.04 that is, and referring to my calculator for this, 2 divided by 0.04 yeah, I should have been able to do that in my head. 50 newtons per meter. If you're interested, what that means is it takes 50 newtons to stretch this spring by a meter. That is question 1.